Hello friends, welcome to weekly lectures. In this session, we are discussing the lattice vibration in solids related to phonon spectra from solid state physics. We are seeing the lattice vibration. This is in general the phonon spectra. Now this is one atom. We generally call it as monoatomic crystal. Then the frequency omega is given by under root 4 beta by m into sine of Ka by 2, that is equal to 2 by root of, it is 2 by A times root of E by rho into sine of Ka by 2. Now here the K is the wave number whose dimension is meter inverse. A is the lattice parameter or lattice constant. Then we have E, which is elasticity. Rho E is given by beta times A, and rho equal to m by A. This is called density, and the velocity of sound or the phonon velocity of sound is given by root of y by d, where y is the Young's modulus. And d is the density. So here rho is the linear density. Then substituting these values, we will get the omega value as 2 by A into Vs. Vs represent the velocity of sound in solid into sine Ka by 2. What is Vs? Vs is velocity of sound in solid. So omega value is written as omega equal to 2 by A Vs into sine Ka by 2. Now we have K is equal to 2 pi by lambda, where lambda is the wavelength, and for large wavelength Ka by 2 will be very small, so we can write sine Ka by 2 is equal to Ka by 2. Thus our frequency omega becomes 2 by A Vs into Ka by 2. So that is equal to K times Vs. Now group velocity is equal to Vg equal to d omega by dk, which will be equal to omega is k Vs, so d omega by dk will be equal to Vs, and the phase velocity Vp is equal to omega by k. Again we get Vs. From this we can write Vg equal to Vp, which implies there is no dispersion. So the medium is non-dispersive medium. Now here's a note: one-dimensional harmonic lattice shows discrete nature of lattice. Discrete nature of lattice. Now at short wavelength, or we write it as high frequency region, omega is equal to root of 2 beta by m sin Ka by 2. Now this is for short wavelength, and we can write Vp, which is the phase velocity given by omega by k, so which will be equal to 1 by k times root of 2 beta by m sin Ka by 2. Similarly, Vg is equal to d omega by dk, which will be equal to root of 2 beta by m. Instead of sine we have cos Ka by 2 times the coefficient of k, that is a by 2. Okay. So here we can write it as Vg not equal to Vp, and so it is dispersive medium. That means at short wavelength or the high frequency region, the one-dimensional lattice, harmonic lattice or monoatomic lattice atomic lattice behaves like a dispersive medium. And on the other hand, for very large wavelength, that means in the lower frequency region, it is a dispersive non-dispersive medium. Now talking about the group velocity Vg, which is equal to a by 2 times root of 2 beta by m cos Ka by 2 at n pi by 2. You can write at plus or minus n pi by 2. You can write the group velocity Vg as equal to 0. Now when n equal to 1, that means at pi by 2 or k is equal to plus pi by 2. Okay, so at k equal to pi by 2 or n equal to 1, this is called first Brillouin zone. Okay, now Vg equal to 0 means there is no transfer of energy at Brillouin zone. So at Brillouin zone there is no transfer of energy, which means the wave is stationary. So this is the important inference that we are making out of this concept. That means at the first Brillouin zone, group velocity Vg is equal to 0, and since the group velocity equal to 0, we can say that there is no transfer of energy, and since there is no transfer of energy, the wave is considered to be a stationary wave. Okay, so once again, going with the frequency of one-dimensional lattice for monoatomic crystal. So we'll write 1D lattice and monoatomic crystal. We have the frequency omega given by root of 2 beta by m sine of Ka by 2. Okay, so now let us write down the maximum omega that is possible here. Maximum omega is when sine of this K by 2 should be equal to pi by 2, so that will be equal to root of 2 beta by m. So sine K by 2 will be equal to 1, so which means Ka by 2 should be equal to n pi by 2. Now here we can write 2 gets cancelled, K is equal to n pi by a, so K equal to n pi by a. So for the first one, for n equal to 1, you will write pi by a. Now we know that K is equal to 2 pi by lambda, and now we say that it is equal to pi by a. Then you can write down the value of lambda is equal to 2 times a. So lambda equal to 2a when the frequency is maximum. Okay, now here there's a small note, that is the one-dimensional monoatomic lattice behaves like a low pass filter or acts as a low pass filter. Now here we write omega max equal to root of 2 beta by m, and corresponding to that we have lambda minimum, because we are arriving or deriving it from the maximum frequency. So lambda minimum will be equal to 2 times a. So this is the minimum wavelength that the monoatomic lattice carries. Here we have the one-dimensional diatomic lattice. Yeah, this is one-dimensional diatomic lattice. And here you have the mass capital M. This is small m. And yeah, the distance between two successive similar type of atom is 2 times A. This is what we need. Yeah. Then the frequency of oscillation is given by omega square is equal to beta times 1 by small m plus 1 by capital M plus or minus beta times root of 1 by m plus 1 by small m whole squared minus 4 sine square Ka by m into small m. Now this plus sign indicates the optical branch of oscillation, and the minus sign represents the acoustic branch. Now this optical branch means it is oscillating with higher frequency, and the acoustic branch means it is oscillating with lower frequency. For the one-dimensional diatomic lattice, the optical branch, right, optical branch is given by omega plus. So omega plus square, as we have discussed, it is equal to beta times 1 by small m plus 1 by capital M plus beta into root of 1 by small m plus 1 by capital M whole square minus 4 sine square Ka by m. Now for k equal to 0, that is at the origin, we have omega plus squared equal to 2 times beta into 1 by m plus 1 by capital M. So omega plus will be equal to root of 2 beta times 1 by small m plus 1 by capital M. Now this is the value, and here we will write the second condition. That means if it is at the zone boundary, so at zone boundary, that means the value of k equal to pi divided by 2a, then omega plus will be equal to root of 2 beta by small m. Coming to the acoustic branch, so acoustic branch for one-dimensional diatomic lattice. we have omega minus is equal to beta into 1 by small m plus 1 by capital M minus beta times root of 1 by small m plus 1 by capital M whole squared minus 4 sine square Ka by m times m. Now at the origin, that means at k equal to 0, we have sine Ka equal to 0, or so let's take it k tending to 0. Ka will be, we can write it as sine Ka equal to k times a. So omega minus will be equal to root of 2 beta by m plus m Ka at the zone boundary. So at the zone boundary, pi by 2a, that means the zone boundary equal to pi by 2a, omega minus equal to root of 2 beta by capital M. So this is the value of omega minus, that is the acoustic branch at k tending to 0, and this is the value of frequency omega minus acoustic branch at the zone boundary pi by 2a. Here the figure depicts the frequency versus the position graph. So this is the position x, and here you have the frequency along the y-axis. Okay. Yeah. Now coming to the region, we have this as the optical region, and here we have acoustic region, or optical branch, or here you can write branch. So this is acoustic branch, and this is the x equal to pi by 2 times a, and here you have x equal to pi by 2a. Then this is the forbidden region, and here you have the value of omega, which is maximum, that is equal to root of 2 beta by m into 1 by m plus 1 by capital M. Okay, so this region you have 2 beta by m, here it is small m, and in the acoustic region you have under root 2 beta by capital M. Okay, so this is how the frequency versus the position of the waves in the crystal lattice behave. Coming to the number of modes of vibration, so number of modes of vibration, you have, suppose if we have number of lattice points,
equal to p, and
Number of lattice point equal to P means number of atoms equal to P. Number of atoms equal to P. Okay. Now let us take the case of one dimension. For one dimension, degree of freedom equal to P. That means if the number of lattice point is P, degree of freedom will be, or number of atoms equal to P, so degree of freedom will be equal to P. Now then the two modes of vibration, that is acoustic and optical frequencies are, since there is degree of freedom P, this implies the total number of modes of vibration. So total modes of vibration will be equal to P. So total modes of vibration equal to P. Now acoustic frequencies or acoustic modes of vibration is 1, and optical modes of vibration, that means number of vibrations which vibrate with optical frequency, is P minus 1. So 1 plus P minus 1 will give you P, which is the total number of vibrations. Now for a degree of freedom P, which means if you are considering about one dimensional lattice which is having P number of atoms, if there are P number of atoms, the degree of freedom for that particular lattice will be equal to P. And if degree of freedom is P, the total mode of vibration is P, and out of that, one will be in the acoustic region or acoustic branch, and P minus 1 vibrations will be in optical branch. Okay. Now similarly for two dimension, there will be degree of freedom of 2P, which means the modes of vibration, total modes of vibration will be total of 2P vibrations, and out of this 2P vibration, acoustic vibration will be 2, and what is remaining, that is optical branch or optical vibrations will be equal to 2P minus 2. Similarly for 3 dimension, if the degree of freedom will be equal to 3P if there is P number of atoms, and total vibrations will be equal to 3P, and acoustic will be equal to 3, and the remaining optical branches, remaining all will go to optical branches, which will be equal to 3P minus 3.